We're on test 11. There's only 2 sections here. Okay, this is one of our shortest tests. And not material, right? Because it's actually been a decent amount of material. What I mean is like shortest the number of sections, obviously, and your problem set questions are pretty short. There's not much work for that. When's your problem set due?
Tomorrow.
Tomorrow. Okay? Yeah, it's tomorrow. So I'm assuming people got started hoping last night. Nobody bugged me. I didn't put the problem set up until yesterday during the 6th period. Let me know next time. I had it all written. I just didn't actually update the file. So if you notice that, please bug me, because that means nobody started until yesterday at least, which is fine. We just finished the sections. But if you notice that ahead of time next time, let me know. 12.2. What was 12.2 all about? What was the idea?
Fluid at rest.
Yeah, it's all about fluids and they're not moving. Very good. It's all about fluid mechanics of things that aren't moving. And like I told you, this is an introductory. It's an introductory to a lot more about fluids you can learn if you study this a little bit further. But we're going to go over the basics. So we started with density. And if you recall, we called this mass density, to be specific, because we talk about the fact that density itself is really just the concentration of something in a given space or area. So there could be a high density of people in a certain region. Or, instead, you could have a high density of mass in a given volume, and therefore that object feels very heavy. Okay? So a good example, I was thinking about this yesterday. Do I have them here? I think I do. Yeah. So these are, I think they're tungsten. They're tungsten weights, and they're really, really dense. So they're much more dense than other types of metal. And you could feel, even more dense than steel, because it adds a lot of weight for like Pinewood Derby cars. If you've ever used that before, you have to have high density and sit in different locations. So density is just the concentration of mass or a volume. They're not that heavy, but if you want to think about density as far as something that would clearly sink in water. What do we know about sinking versus floating? What are the things you know about sinking versus floating?
Sinking is the object is denser than the liquid it's in, while it's floating at equilibrium.
Okay, so we start with that for density. Very good. And that's what I'm referring to here as density. And for floating, what do we know? What's actually, there are really 2 possibilities. There's floating and then there's that in between. For floating specifically, it's at the top.
Is that equilibrium?
But for density just now. We'll get to just for density.
It's less dense than the object is floating on.
So the object is less dense than the fluid it's floating on. Okay, so in these cases, we can see that we have changes in density. Now, if you have 3 layers of different fluids, so if you have oil and you have water and then, vinegar maybe? I think vinegar and oil are different densities. You'll see them separate from one another in different layers. I think I mentioned this yeah, good. In this class I talked about that. That's how you can see how dense something is. That's a great kind of question I could ask on a test about relative densities of materials and understanding where they are. So if you have 3 or 4 layers of a fluid and you drop an object in it, wherever it settles is where the actual density of the object lies. So if it settles in the oil, there's a good chance its density is the same of that of oil. If it stops when it gets to water, its density is probably the same as the water. But you want several different materials and different fluids to be different, like strata, or like levels of clouds almost. Okay, think of it that way. For equilibrium, Matei talked about for floating, he said there's equilibrium. What does he mean by that? When it's floating, there's equilibrium. What does that actually mean? Yeah. So we've got the weight pushing down, and we've got buoyancy pushing back up. And they're balanced with one another. They're perfectly balanced in this state when it's floating at the top. Okay, when it's floating at the top. So we know here that we have FB minus FG, and that equals 0. That equals 0. The caveat, but the change to that is to think about that scenario where something would be floating, but it's being held underwater. Okay, so think about a beach ball we talked about in class several times. You hold the beach ball underwater, the buoyant force actually exceeds gravity when you're holding it there. Okay, the amount you're pushing down with exceeds, so when you let go, suddenly you have this net force upward, so the beach ball shoots out of the water. Okay, so there can be an imbalance of force when something is either held down or tethered down under the fluid itself. If it sinks to the bottom completely, you definitely know something. If it sinks to the bottom, what's the reason it would sink?
The overall force is downward.
Overall force is downward. So we could say that in this case, Fg is greater than Fb. We don't know how much greater it is, but we know that it's greater than. You okay?
Oh, I was trying to learn that.
Ah, okay. That's fine. I didn't know we had it. So Fg would show up as like a longer vector, and Fb on the free body diagram would be a short vector. Okay, so we have these two scenarios that we're really focusing on in this entire section. Now, it's possible we ask the question such as, what's the apparent weight of the object when it's underwater? What's the apparent weight? And apparent weight, what does that mean as a physical entity? What is apparent weight? If you ask somebody what your apparent weight feels like, that may give you a little more of a hint.
Like how you feel inside of the liquid, because it's not your actual weight.
Very good. It's the difference between your actual weight and the buoyant force. Again, look at the free body diagram. How much do you actually weigh? You weigh whatever Fg is. Agreed? Whatever Fg is, that's your weight. But if we look here, we can see that Fb, that counters Fg by a little bit. So if your weight is normally 100 pounds and the buoyant force is, say, 40 pounds, you feel like you weigh only 60 pounds. And that comes from F net. So let's jot that down. F net, remember, equals ma, but F net is really the sum of the forces. Well, in reality here, we've got Fb pushing up and we've got Fg pushing down. So the difference between those two values is what F net is. It's going to be a negative number for sure. Does everybody agree with that? Why is F net going to be negative? The object is being pulled down. Again, Fb might be a number like 20 or some value, whereas your weight itself might be like 90 newtons or 90 pounds. It doesn't matter. Okay, so the net force in this case would be negative 70. So the idea is that the net force acting on an object, well, that's the apparent weight the object feels like. So you feel like you weigh 70 pounds because the buoyant force is helping you with 20 pounds.
So incidentally, is there an actual value placed on it since it won't be a negative?
Sure, you could put absolute value around. I think in class I did that, right? I threw absolute value around at some point to show that the magnitude of your weight is what matters. We know it acts down. We know it acts down. So you could put absolute value around that. Right, could you open that window?
Yeah.
Thanks. All right. We don't have to worry about this scenario here. Take a look, please. When it's floating, because when it's floating, what do you feel like you weigh when you're floating? Nothing. And that's why, look, right here. It's 0. It's still Fb minus Fg. It's still Fb minus Fg. It's the exact same equation of motion. Look at these two spots. It's identical, right? They're the same. But this one equals 0, whereas this one is equal to some value, F net, your apparent weight. What else do we know about volume when an object sinks versus volume when an object is still floating? And by volume, I mean VO and VF. What's their relationship? What are they? Yeah.
When an object is sinking, VO is equal to VF.
So when it's fully submerged, either sinking or in that in-between stage, absolutely right. Okay, now, that's the case for that one scenario. What about when it's floating? How do you explain that? Somebody else, I know Joanne knows this one. How about when it's floating? This is one that's a little bit tricky. What would you say in words? Go ahead.
The volume of the object when it's floating could be that of half of it, or it could be a third. Or
So a what? What's the word for that? Half, third, what are those called? So it's a fraction of, go ahead.
of the fluid or volume, or a fraction of the object.
Thank you. So the amount of fluid displaced will be a fraction of, so less than or equal to, less than really I should say if it's actually floating, less than the actual volume of the object. Think about it for a second. Okay, I'll draw you two diagrams. So here's the water level in the left diagram. Here's the object down here. It's fully submerged underneath the water. So how much is submerged? That's what VF is. Remember, if you don't know this by now, please write this down. VF, we call it, ready? There's two ways to name it. I've been calling it all chapter the volume of the fluid displaced. It's really just how much of it is underwater. VF is just the volume of the object that's submerged. However much of the object that is submerged. That's what VF is. It's the amount of the volume of the object that is submerged. VO, obviously, is the actual volume of the object. So in the second case, we have, obviously, the object is floating, so part of it is exposed from being submerged. So as a result, here, we know that this part right here, I'll shade it in so you guys can see, this is VF. Whereas in this case, the whole thing is VF. If you forget this fact, I'm not going to lie to you. If you forget this, you're going to really struggle on the math problem for this on the test. Okay, this leads us into the math problem that we're going to be covering. Is that clear what I'm saying? Okay, we did two problems where one thing was tethered and inflated, another one where there was a ball bearing and how much of it was exposed out of the water. You need these facts to do this. Yes?
So like if we're doing the math on, it would be to find VF. Right? We would.
It could be find VF. It could be find the amount of the object that's above the water floating, which means you would have to figure out the total volume and subtract VF to see how much is left up here. That could be the problem. That's what we did in class. It could be nothing to do with finding VF, Ernest. But you probably have to use VF during the problem. Okay? So let's look at an example. Are we clear on the theory we've gone over? This is all the theory of the beginning of 12.2. I think personally that this is going to be the hardest part of the test. That's why I'm focusing on this a lot right now. Okay? So let me just go to the next slide to do this. Any questions on this stuff so far? Any other questions before I move on to an example? Ernest, go ahead.
So like the VF and VO, I don't know. So VF is the actual object.
How much of it submerged is VF?
Oh, and VO is the actual object.
Correct.
Okay.
It's called F because it's the volume of the fluid F displaced, but it simply means how much of it is underwater. Okay? If 50% of the object's underwater, then VO and VF are equal to each other. They're both VF is equal to how much is above the water. It would be whatever half of VO is. Okay? All right, let's go to a math example. I just went up on the spot. Let's take a look at an example where an object is sunk in the water. Okay? So let's say the object is under the water. It's sunk down to the bottom. We'll say that the density of the object itself, it's got to be greater than water. And I know water is 1,000, salt water is 1,025. So for the sake of this, I'll say the object's density is 1,500 kilograms per cubic meter. The density of salt water is 1,025. Again, do you need to memorize these?
No.
Good. You do not have to memorize these. Okay, I'll give you the values, or you'll be given a table, and you just look them up in the table on the test. One of those two things. All right. So you're given the value of the density of the object and the density of the fluid. If let's say we know the volume of the object itself, okay? We know the volume of the object. It happens to be, well, it doesn't matter. Let's say in this case, 0.1 cubic meters. Okay, 0.1 cubic meters. Determine, and this is the kind of way it's going to be asked on the test. Okay, I'm going to give you steps along the way to kind of progress you through the problem. Determine first the weight of the object, then determine the buoyant force, and then determine the apparent weight. We did something like this in class, but the object was floating, so it was easy. If it's floating, what's the apparent weight? If it's floating, what do you feel like? Zero. I thought you said zero. You said, God bless you? I think you said zero. I'm like, that's it right there. The apparent weight is zero if you're floating. Okay, God bless you. And that, in case, is where the buoyant force and the weight balance each other. But since this object has sunk, when I draw my free body diagram up here, I know to make FG greater than or less than FB. Good. Okay, there's FB right there. So this problem is set up. It's all ready to go. It really is. It's not a hard problem at this point. You know what gets difficult? Let me explain what gets difficult here. Plugging in for the unknowns, because the formulas are a little bit funky here. So let's get into what we've got. We know that F net equals ma. I don't know anything about the mass or acceleration, okay, but I can at least plug in for F net and figure that part out. F net is FB minus FG. Well, take a look. FB and FG, isn't that just part A and B here? And then what's part C? How do I find part C? Once I get parts A and B, this is how you need to think about these problems before you even get to the math. A and B, that's FB and FG. We're done. We've got it really already. We can just plug in and solve. What's part C?
Isn't it the same thing? Isn't it, we subtract the buoyancy and the actual?
It's the difference between these two. So do I even care about M times A in this problem? No, I don't. So if I want to just go like this and write this out instead of writing F net equals MA for this problem, because nothing's given about the acceleration, okay? It's nothing that we have to worry about in this case. So we're literally just looking at the difference between those two. We're eventually solving for F net. But along the way, we have to go through the process of finding each of these. FB, what's the formula? Come on, quick. You should know this by now. We've done enough of them. Go for it.
Density of fluid times volume of fluid times gravity.
FG, what's the formula? Always the first one we can start with. We can go to the answer right away, or we can start with the original formula, which we can always really do. I'll tell you, what's the original formula for FG always? MG. Now I'm putting an O. I keep doing that this chapter. What does the O stand for? Object. Okay, this needs to be like everybody answering this kind of question, guys. We've done enough of these. We did this with the math problems also yesterday. Now, recall that the formula for density is mass over volume. So if I solve for mass, it's density times volume. So replace mass with density times volume. Everything else gets carried down. The problem is just plug and chug at this point. You know everything. Everything in the problem is given to you. We need to make one conjecture. What is that conjecture? It's one thing we have to state that we have not stated yet. Look at what's given in this problem. I'll go even further back. Okay, look at all the things that are given in this problem. What's the one thing we haven't written down yet that we need to write down for a problem where an object sinks? Very good. The key fact here, we haven't written it down, VF and VO are the same thing. Remember, VF is how much of it's submerged. Well, how much of it's submerged? The whole thing. So VF and VO are the same. So that's something that we want to know. We wrote that down in the previous slide, but we need to maybe jot that down earlier in the problem. Okay, so write that down earlier as one of your givens. So now we know all the numbers. We can plug everything in. F net equals. Now, we're going to want to see these values, so we don't want to compute right away. Yes, Lauren?
So VF and VO and the objects.
Correct. Because VF is how much of it's submerged. If it's floating, only part of it is submerged, right? So we'd say it's a fraction of that value if it's floating. 1025.1, 9.81 minus 1,000. Sorry, 1,500, sorry.
So I feel that's where you get 0.1 from remember VO.
Yeah, it's the volume of the object. And maybe I should use units here, right? I should do that, but I didn't, just so you can see what the values are. But look at the formula above, right? Here's what we've got in this problem. Now, let me point something out real quick, please. Listen. You could factor out 0.1 and 9.81 to the front, find the difference between 1025 and 1,500, and then multiply back out, but then you wouldn't be able to determine the value of this and this, which are parts A and B. See what I'm saying? So this is not a scenario where you want to factor these out in front. Do not factor these four values out in front. Okay, so go ahead and evaluate them independently. Find out FB, whatever you get goes here, minus FG, which goes here. That's part A and B, and then the difference between them is part C.
Have we done a question with acceleration?
We have not, but it could easily be done if I say the object is being held down and then it's released, find the acceleration, you would find the net force, take a look at the board, and then you would go here and solve for A. So this difference here would go in for F net. You would need to have the mass, so you'd have to plug in rho V for the mass like you did here. Remember the mass was here, you plug in rho V, and you'd solve for A. Yep, that's a great question to ask, Gabe. Okay, you could solve for acceleration in one of these problems also. What do I get for these values? Give me numbers. Give me numbers. What's the buoyant force first? What's the buoyant force? Amaya, go.
4,005.
And what's the weight?
1,471.
It makes sense, obviously, right? Remember we talked about this? No, actually, it was the other class. I talked about sanity of answers. My calculus teacher used to do a what you guys? Used to do a sanity. Clearly, I'm insane. Used to do a sanity check, and in this case, it makes sense that the weight is greater than the buoyant force because it's sunk. Okay, so we have answers for part A and B. This is part A right here. There's the answer. This is part B. There's the answer. And this is going to be part C right here, whatever the difference is in those values. What do I get as the exact value for these two? It really doesn't matter. It's an arbitrary number, right? Thank you. Okay? So that's how much you feel like you weigh. Around a third of your weight. Everybody see that? Take a look, please. Estimate. Here, 1471. Cut that in 3, or around 500. Is around 500. So you feel like you weigh, or this object feels like it weighs about a third of its actual weight. So when you're swimming, you're only lifting a third of your weight in this scenario, under this fluid. Okay? All right. After that, in 12.2, we talked about two things. Pressure in general equaling force over area. Let's pause before we go further. These things are indirectly related. So if I have a little bit of area, like the tip of a pin I talked about, you could pop a balloon because very little area creates high pressure. But if you take your finger and tap on a balloon, does it pop? Because your finger, the contact area is much greater than a little pin. A pin has such a small contact area. Some of you, or one of you also asked about, is that how you can cut through like food with a knife? Same thing, really. You call something sharp, don't you? What does razor sharp mean? It simply means that the amount of area of that tip is so small that it's such a great pressure. And when you put even a little bit of force, it's such a high pressure. Because again, small area means high pressure, indirect variation. If you have more force, if you take somebody like your younger brother and put them on your shoulders, and now it's more force acting down, there's more pressure acting on your body. Literally more pressure. Okay, because it's more force over the same area. The area is whatever the area of the bottom of your shoes would be. That's the area. Now, we talked about how this is related to Pascal's principle with a hydraulic press saying the following. I don't think, please check actually right now, I don't think I give you this formula. I'm pretty sure that I know I give you this formula. But do I give you the other two at all on the formula sheet?
I think so.
I don't think I do, actually. I'm pretty sure I don't. Okay, here's the reason why. Let me explain. Just like I didn't give you mv squared over r. It's a function of other formulas that are already there. I mean, this is the formula right here. This is Pascal's principle. Pascal happens to be the unit of pressure, and he came up with this principle about pressure. And the idea is that in a closed container, the pressure transmitted by the fluid is equal to all the parts of the container. So we looked at a press, and we looked at like a lift. There's this fluid in the chamber. It's called a hydraulic lift. And the idea is this, ready? Here's the piston itself, and here's the other piston. If you press down on this end, and it pushes down, like, you know what a plunger is? Ever seen? Oh, here's a great example. You go to the doctor, you get an injection for a vaccination. What are they pushing down on? You know what that's called, the needle? It's called a plunger. It's a piston. I know, come on. Don't think about drugs, think about vaccinations. Because you went like, ooh. You don't like needles?
What?
Do you not like needles?
No.
All right. So anyway, a plunger, you push down on the plunger and it injects the vaccination into your arm. That's what you're doing here. Literally, look at this, please. You're pushing down on the plunger on the right side, which forces the fluid to go somewhere. Where can it go? It can only go to the other side. And it forces this piston to rise up. So if you put an object over here, usually it's a car. You put a car on a hydraulic press. My illustrations are wonderful. It's like a Jetson car, I don't know. The car itself gets lifted up off of the whatever, table, ground, whatever you call it. Okay, usually there's like a metal rod that connects with the car's axle and lifts it up so the mechanic can slide underneath and look at what's happening under the car. It's in an auto shop that this happens. The idea behind it is that there's a mechanical advantage. Here's your formula. Let's say, I'm not going to do a math problem for this. These are really easy, but I want to talk about mechanical advantage. Let's say that the amount of force you apply is only 25 newtons. But the weight of the car lifts. The weight of the car is 600 newtons. What's the mechanical advantage in this circumstance? Mechanical advantage is the factor of increase you get from using this tool. So how much is the factor of increase that you get out of this? You only put 25 in, but you get 600 out. You're literally pushing down with only 25 newtons of force, but 600 can be lifted. It's amazing to think about this. What's the mechanical advantage? Not subtract, divide. Factor of increase, Lauren, if you subtract, that's finding the overall increase. That's what subtraction would be. The overall increase would be 575. But the factor of increase is 24. So the mechanical advantage, write this down please, is your output over your input. Again, not a formula given, but something I mentioned in class but didn't go into formulas with. 600 over 25, which is 24 times greater. 24 times more weight is lifted than what you put into it. It's the same thing as using a torque wrench. Remember I asked the question on an old test? You use a cheater bar, and a cheater bar extends the length of a wrench by sliding a metal pipe over the wrench. And now you can get more leverage, kind of like, what is that called that you use to break into like a window? Crowbar, thank you. Crowbars are used to break in or to get leverage, really. Not, I should say break in. But if you need to get a door or the latch of a cabinet open or something that's stuck, use a crowbar because you get leverage on it. Okay? If you want to remove a nail that's stuck in the wall and the back of a hammer isn't enough, use a crowbar, you get leverage. Mechanical advantage. After this, we then talked about pressure underneath the surface of a fluid. This is the overall pressure. Another word for that is total. This is the pressure from the atmosphere. Atmospheric pressure. It's an I at the end there. Atmospheric pressure. This is called gauge pressure. This is from the fluid. In this case, it's really a liquid. I should say liquid. Because we know that we're underneath a liquid in this case. Okay, it's underneath the surface of a liquid that we're talking about here. So the gauge pressure is the pressure that the water itself, in this case water, exerts on you. The atmospheric pressure is literally the air in the atmosphere as a fluid, God bless you, as a fluid weighing down on you. So you have to be underneath a liquid to have gauge pressure. Gauge pressure is from a liquid. I guess it could be from a gas also. I shouldn't say liquid necessarily. But in this case, we're talking about being underneath water, okay? Specifically, yes.
So that mean that that wouldn't be constant. Like you can make it, just give us around, right?
This is always this number here, and then this is whatever you turn out to be depending on how far you go.
But like for a problem with it, every big problem would be like they're in that, I don't know, some random atmosphere.
Oh, sure. And then PO could be something else.
Yeah.
Absolutely. You're on the moon where atmospheric pressure is 5 times 10 to the 2. You replace that number with 5 times 10 to the 2. Yeah. I'm going to keep it on Earth, though. I'll tell you that now. So you don't have to worry. But yeah, on other planets, atmospheric pressure is different. Yep. So really, this is a function of what? What is this? You did this in your lab, right? Remember yesterday in the lab? What is this a function of? 3 things. 3 things. They're right there in the formula. What are they? Give me one of them. Overall pressure is a function of 3 things. Assuming we're on the Earth, Overall pressure is a function of three things. Redeem yourself. Look at the formula. Come on.
The
Assuming we're on the Earth, so that doesn't change. It's a function of three things. Give me one of them.
height.
Height, or in this case, help him. It's not height, really. It's the depth of the water. Remember, H is the height of the water above you. So we use the word depth, even though it's H. Okay? Gravity on that planet, Earth, 9.81. And the density of the fluid. If you need to write that down, write it down, guys. Or the liquid, fluid, whatever. This is the density, in this case, of water. So water happens to be 1,000. So if you're in the water, it's 1,000. If it's salt water, it's 1,025. Whatever else could be given. 9.81 on Earth. And whatever the height is. And this, I'll just write down depth. So really, we're looking at the pressure as a function of a depth for the most part. Okay, because you're not... When's the next time you're going to be submerged under honey? Anybody ever been submerged under honey before? I hope not, right? That'd be terrible. Gosh, it'd be scary. Imagine trying to swim out of that.
No.
Imagine trying to swim out of honey if you're like 10 feet under. It'd freak me out big time. Is it freaking you out? Are you having like a nightmare in your head?
No, not
You ever
that
seen
kind of
Fear
thing.
Factor?
Die.
It's like quicksand. Quicksand's very viscous. I mean, I've seen it when I was a kid, but like, I never saw that. That'd be a cool one, right? Submerged under honey. I don't know. I've never actually looked at the mechanics behind it. I'm guessing it's extremely viscous and you can't swim out of it.
Like, it has to be really deep, right? And that's why you fall through it. Yeah, I do.
I wonder if it's not very dense, which is why you sink to the bottom. Maybe it's not dense, but very viscous. So maybe it's viscous so you can't swim out, but somehow it's not dense.
What makes it like
Google, come on. Ask it right now, I'm curious. All right, next question, or next topic, was the continuity. We talked about surface tension, how surface tension works as a membrane. No math involved there. Next topic was the continuity equation, which told us the following. And this is on your formula sheet. But recall that this is also equal to the volumetric flow rate. So you could have a third part to this formula. We did not, I don't think, go over this in this class, actually, this last part. But I did go over it in the other class, and it's in the second half of the video, and I think I talked about it in the video also. Volumetric flow rate, remember your units. I know for a fact I talked about units in this class. I reminded you guys that area is meters squared, and that velocity is meters per second. So what do these units become when you multiply? Look up, come on people, look up. What do these units become when you multiply them? What does it become? Ernest?
Meters cubed over second.
And what's meters cubed a measurement of? And what's seconds a measurement of? Take a look. Please take a look. So this is proving to us that AV could also be equal to capital V over T. Not lowercase v, little v's here. This here is velocity here and here. This is volume over here. So if you want to, jot this down right now, please. You can write this down also. This is the alternate form to the formula right here. So the two forms of the formula are in boxes. I extended the first one so you could see that. But if you're writing them down, the one that's in the box at the bottom is not given on your formula sheet. Because again, the theory is what you need to know. You should know that this means, write it down please, that the volumetric flow rate is constant. Therefore, you could set this equal to volume over time, because volumetric flow rate means volume over time. How much volume has passed, how much volume of the fluid is flowing in a given time period. Usually in the US, we measure that in gallons per minute. Okay? At the gas station, when you pump up, it's in gallons per minute. Here, it happens to be in cubic meters per second. It's the same unit, really. It's just a different value. Okay? It's still a volume over a time period. Anybody know the bell for E-Day?
27.
What is it?
27.
27. Thank you. Is this the day where it's all sevens and twos?
Yeah.
Sevens and twos? Okay. I think that's what it was. I remember somebody saying that. Caroline.
The quicksand is because water can't escape sand, so it creates a liquefied fluid. And that's why it can't support weight. So you're supposed to stay still and try to float.
Wow. But it's just water and sand. That's all it is. Nothing more than that. And some salt. Interesting. I would love to see math behind it, though. I'm curious if somebody... I guarantee you... So you want to laugh? You know Pinewood Derbies? You know what those are in Boy Scouts?
Oh, yeah.
You have the little block of wood. You have to carve it. And you attach wheels. And the idea is to get the fastest car by placing mass in strategic locations. So you would never think that that's a big deal. It's a Boy Scouts competition. Somebody in an engineering university, I think at MIT, did a research paper or a whole thesis on the correct design and placement of masses, the design of the axles, the carving of the block of wood for Pinewood derbies. They did all the math to optimize the velocity, to maximize velocity and minimize time. So I guarantee you actually that there's a paper in some journal article that by some peer-reviewed engineering university on quicksand. That's what I'd be interested to see, how it really works, the mechanics behind it, you know? Because it's got to be more, I get, it has to do with density and viscosity. I'm guessing those two factors. That would be my guess right off the bat. All right, so the last part we want to talk about is Bernoulli's principle. And Bernoulli's principle, what is the indirect variation that exists there? Who remembers? Bernoulli's principle has to do with indirect variation. What is it specifically?
The pressure, the fact that you have a lower pressure at higher velocities
And
higher pressures at higher pressures at lower velocities.
good.
Makes something lift.
Tonight, in your problem set, there's a question that says, take a ping pong ball, if you have a ping pong ball at home. Okay, take a ping pong ball and a hair dryer. Put the hair dryer over here. Okay, from the hair dryer, turn it on at an angle toward the ping pong ball. If you actually get it at the right angle, it will float in the air. True story. No joke. This will actually work. What will happen is the velocity of the air on the top will be much faster, creating a low pressure. I'm writing my finger. My pencil's charging. On the bottom, the velocity will be slower, creating a higher pressure. If there's more pressure below than above, it creates what we call lift force. Very good. Okay? This will literally work. It's one of your problem set questions. I kind of just gave you the answer there, right? But I want you to actually just try it yourself. Okay, if you can get it to work and videotape it, I'll give you 2 bonus points on the next test.
Oh, so it's not.
Out of 40.
What was that?
Okay, if you can do this and get it to work and videotape yourself doing it.
So it's not like this. 'Cause we did yesterday. Look it up, like see how it would work.
So take a look at what Will's showing. This one works also, but it's supposed to work this way as well, believe it or not, which is crazy. That one I can make sense of. Can you hold it up? Okay, if you hold the dryer literally below it vertically. But if you do it at a horizontal, a little above the horizontal, it should also work. That's what I want to see. That one is a little more obvious. If you can do that one, I'll give you 1 point at least so you can see that. If you can get this one to work, I'll give you 2 points. Okay, on tomorrow's test. Or Monday's test.
What are you doing?
That's insane.
My hair dryer.
Borrow one from somebody. Figure it out. You can go to any store and get it for like 99 cents, a pack of like 5 of them, and even like a deli. Okay? So maybe a couple of you buy them, split them, and each take 1 ping pong ball. Use a ping pong ball. I think that'll work best, personally. I'm pretty sure a ping pong ball will work for this experiment. I have not tried it. I just saw it was a question in your problem set, so. Yeah, I don't know. It says a little bit above the horizontal. It's not going to be horizontal, so it's tilted. See how I tilted it? Okay? Questions you might have at this point. We have 2 minutes. 2 minutes. Questions you might have still, yeah. Yeah.
So those are the type of math problems.
So I gave you I gave you the hardest type of math problem to expect. But you could also expect to have one relating, if you recall, this. You could recall something with this. Okay, those are definitely ones. You could use maybe this for a math problem. Any of those formulas. I did an example of the hardest one today on purpose. Okay? Please, if you want to review these types of questions and problems, look at the last 4 examples from 12E that I either recorded from the other class or at the solution that's posted online.
I was just